Recording. Okay, everything is now recorded. Okay, yeah, let's continue. So new concept, stopping time. Stopping time. Let's consider the case of discrete time. Let's consider discrete time case. Discrete time case. So we have t that is probably 0, 1, 2, 3, and so on. We'd like to introduce a special random variable tau, which is special in the following way. It can take values 0, 1, 2, 3, or it may be never, special value plus infinity. So stopping time is a moment of time, random moment of time with some properties. First idea, that it may have a special value, value plus infinity. That means never. So I will go home when the first bus will arrive. It may be in 1 hour, in 2 hours, in 3 hours, or never. Maybe the buses will never arrive. Okay. And second property, we say that tau is a stopping time. Tau is a stopping time with respect to filtration. FT. If oh no, it's not like a definition. No, let's describe it more. Sorry. Let me write in a more systematic way. Okay. I will have a definition and the comment because I have mixed comment with definition and it's a bad way. So we say tau random variable is a stopping time with respect to filtration FT if first property it takes values from the set of possible times plus special value never, and second property that for any t the event tau is less or equal than t belongs to the sigma algebra ft. Okay, and now here I will write comments. So I will write comments. First comment that we interpret plus infinity as never. So probably the first time when the share price will hit the price 200 rubles. So it may be this day, tomorrow, after 2 days, after 3 days, or never. Yeah, something may never happen. And this idea is so the first idea is just we have a special value that we interpret as never, and the second idea is that in plain words, we mean that at any moment of time t, it is possible to check whether t has already happened. Yeah, happened. Okay, at any moment of time, I can say, what does it mean? The event tau less then t belongs to ft. And it means my information is sufficient to check whether t is in the past. Okay, I have enough information to check whether t is in past or in future. So let's provide some intuitive examples. Oh, what is happening? Okay, let's provide some intuitive examples of stopping times. I will provide you two examples. One example will be a stopping time, and the other will not be a stopping time. So let's develop intuition. So imagine that you observe the price of a share. So imagine that ST is a share price at T. And imagine that you know nothing more. So your information is described by S1, S2, S3, ST. So that means ST is a sequence of random variables. They are obviously dependent, but I don't care about their dependency for the moment. I have my information is limited to the observations of S1, S2, and so on. So I don't know, for example, some process YT or ZT. So I know I observe only ST. This is my information. And I propose you two moments of time, two random moments of time. The first one, tau1, is the time erg maximum by t in from 1 to 100 of ft, and tau2 is a minimum t such that st is equal to S1 plus 100. So I propose you two moments of time. So my question is check first intuitively which one, tau1 or tau2, is a stopping time and which one is not. So once again, ST is some random process, let it be the share price at time t. And I have two moments of time. They are both random moments of time, but the name stopping time can be applicable to only one of these random moments. Tau1 or tau2? Which one is a stopping time, which one is not, and why? Okay, let's check our intuition. At any moment of time, it is possible to check that tau is in the past. Okay, I provide you some pictures. Let's consider first tau1. This is T. This is ST. These are moments 0, 1, 100, 101. I will draw a continuous curve because I'm a little bit lazy, but obviously we have here a discrete time process, so it would be better to write points, but I will draw a continuous curve to simplify. This is at 0, so something that happens. Tau1 is the erg so it's erg maximum of ST. So erg maximum of ST by T in the segment from 1 to 100. So where is tau 1? So I search for the biggest, for the highest value of ST. Here it is, the highest value of ST. And arg maximum is here. So this is tau 1. Okay? Tau 1 is a random moment of time. Okay? But imagine that you are somewhere here. Imagine that now we're here. Can we be sure that tau 1 is in the past? So if current time we are located on the green point, as a green point on the time axis, can we be sure that tau 1 is in the past?
Yes, we can be.
No. If you are here, you don't know the future yet. So this part of the plot, you don't know it yet. And you cannot be sure that tau 1 is in the past. Because
Why cannot we be sure? Because we choose t from 1 to 100 at the moment of 101.
Yeah,
we know for sure that it happened
imagine
before.
This is moment. Sorry, imagine this is moment. Let's say 95. This is t equal to 95. Can you be sure at the moment 95 that tau 1 is in the past?
No.
No. And in the definition, for every t, you should be sure that the tau is in the past. So in the official definition, the requirement says that for any t, you should be able to answer the question, tau is in the past. So this is tau is in the past. Your information you have at time t should be sufficient to say whether tau is in the past. And I provide you a specific example of t. I say t is equal to 95, and your information is not sufficient to be sure that tau 1 is in the past, because it may happen. It may happen. It will not happen. Yeah, given if I am like a god and I knew the full trajectory of my process from the beginning till the end. So okay, I know. But given information at f95, I'm not sure yet. Maybe it will sharply go up. Yeah, and in this case, the arg maximum will be to the right. And if I consider tau 2, this will never happen. Because if I look at tau 2, this is a minimal value of t such that st is s1 plus 100. And imagine this. This is t, this is s1, this is s1 plus 100. And let me draw a trajectory. So I have a random trajectory of my process. And where is tau 1? Tau 1, oh, sorry, tau 2. Tau 2 is here, the minimal moment of time, such that st is s1 plus 100. And let's consider some green moments of time. Let's consider this moment of time, t1. At t1, do you know whether tau 2 is in the past?
Yes.
Yes, we know.
Yes, we know that tau 2 is not in the past. Yeah. Let's consider a time moment t2. At moment time t2, do you know that tau 2 is in the past?
Yes.
Yes.
You know the part of trajectory that is sufficient to check whether the tau 2 is in the past. Okay. So according to the definition, you should be always able to check whether the event is in the past. Tau is less than t, that means tau is in the past. And ft is your knowledge, your information at time t. So you are able to check whether tau is in the past.
Excuse me. Can the event unhappen? So it was not, then it happened, then it unhappened.
No.
Okay, thank you.
Because if tau is less than 5, then it follows that tau is less than 10. In our case, no. If you consider some event that is, but these are different events. So if you consider like something like st is, let's say, greater than 10, but it's not, it may be true, so it may be okay for t equal to 1, and it may be false for t equal to 5. That may happen, but these are different events. So S1 greater than 10 and S5 greater than 10. This is some event A1, and this is some event, let's say A, let's say B. So, and these are two events, A and B. And it may be that one has happened and the other has not happened, but every event either happens, either not. It's not possible to be in a quantum state like it has half happened, half not happened. One of two alternatives is right. Okay, let's move on. So in my example, which one is stopping time, tau 1 or tau 2?
Tau 2.
Tau 2.
Yeah, tau 2 is the stopping time. And tau 1 is just a random variable. Tau 1 is a random variable, but it's, so stopping time is a special type of random variable. Not every variable is a stopping time. But tau 1 is a honest random variable. We may study its properties, calculate its expected value, variance. It's a honest random variable, but it's not called stopping time. Okay, let's move on. So optional stopping time theorem. Optional stopping time theorem. Let's provide intuition first, as always. Roughly, if you don't, so first intuitively, if you don't wait infinite time, so if your martingale is not, so let's intuition first, let me write it. So if you, sorry, if you don't wait too long and the process xt, if you don't wait too long and the process is t, and the process is t is is not too big, yeah, let's not too big, then you cannot make money. So, and the process results of first intuition. If you don't wait too long and the process is not too big, then you cannot make money by stopping a martingale. So the intuition is very easy. So if MT is a martingale, so what do we mean by a martingale? We mean that expected value of MT given Fs should be equal to what?
MT.
MS for
MS.
any
MS.
Less than T.
less than T, yes.
Mass.
Current
MS,
value.
the current value. Okay, so if MT is a martingale, and imagine you stop it. So you say tau is a stopping time, and M tau is the value of a martingale at a stopping time. So you decide, now I quit the game. It's time to have a lunch. And so I break my lecture, and M tau is, let's say, the number of theorems we have proven. Yeah. So M tau is the value of a martingale at the moment tau. So tau is a random moment of time, and M tau is my fortune when I leave the game. But my game is fair. It's a martingale. It may go up. My fortune may go up, may go down. And I'm not looking into the future. So strategies like, let's check whether tomorrow MT will be higher than today. If it will be higher, then we wait tomorrow. If it will be lower, we quit today. So this strategy is ruled out by the requirement that tau is a stopping time. Such forward-looking strategies are ruled out. So in this case, basically expected value, so intuition step 2, expected value of M tau is just expected value of M0. So basically, if you don't look into the future, if you are playing a fair game, then your fortune at the moment when you quit tau, the expected value is just the same as expected value at the beginning of the game. And now the formal statement. We need some technical conditions. So once again, if first MT is a martingale with respect to filtration FT, tau is a stopping time with respect to the same filtration FT. Oh, sorry, stopping time with respect to same filtration FT. What else do we need? And we need at least one of additional conditions is satisfied. Additional conditions is satisfied, and we have some additional conditions. A1, that tau is bounded. That means there is a number m such that tau is less or equal to m. Second additional condition as that probability that tau is less than infinity is 1. And the process m minimum tau and t is bounded. Or maybe third alternative, that expected value of t is less than infinity, and conditional expected value of it would be easy to introduce a notation. Let me write something like, I will use it once again. So it will be m tilde equal to m minimum t and tau. And here I need the difference, delta m tau, given f, given fs. Yeah. Oh, it's better to write mt plus 1 sufficient. Ft is less than infinity. And is bounded. Yeah. Okay. Yeah, that's fine. I like these technical conditions. Yeah. Then it's a theorem. As then, yes, if then expected value of m tau is expected value of m0. That's fine. Okay, let's apply this theorem. Maybe we will not always check that the theorem can be applied because it's a little bit technical. It takes maybe a lot of time, but I need to state theorem. I have stated it, so let's apply it.
May I ask a question?
Yeah.
Could you please once again explain why the expected value of m tau equals to m0, but not, for instance, for expected value of m tau minus 1? Or it should be, I mean, correct to say even in case when tau is 1, for instance.
Sorry, I have no statement about expected value of m tau minus 1. It's another science, so we can do it. But my statement is about that. What is your questions once again?
Yeah, my question is why it's m0, not any other number, not any other m.
Yeah, you may say expected value of m1, expected value of m2. We know that for a martingale it's the same.
Yeah, okay, thank you. That makes sense. Yeah, thank you.
But in normal conditions, it's easy to check this one because normally starting value is given and it starts fluctuating. And when you calculate something and you know that the first value is 5, then it's easy to make equations to calculate. So yeah, that's true for any other t, but in a lot of applications, you just observe first value. So you know the current price of share is 100 rubles, so it's easier just to work with. Easy.
Thank you.
And these are future values that are random. So, okay, first let's apply this theorem, and then we will see what will happen. Okay, for example, let's example. As far as I remember, we have considered the process like, just let me look. During the class, we have considered, let me check to start. Yeah, we have considered, I will just copy the result. Yes. So it's exercise. We have x1, x2, and so on, because we have already calculated, we have already created martingales. Each x has two possible values, 1 and -1. This is probability that x is v. Yeah, 0, 4, 0, 6. I think with the first group we have considered values 0, 4, and 0, 6, and with the second one like 0, 3, 0, 7, but the logic is the same. And we have created Sn like x1 plus x2 plus xn with initial value 0. And we have proven, so we have already done. We have proven that the process, so, and we have filtration ft is just we observe xt, all previous values. And we have already proven that we have two processes. The first one is zt equal to st minus 0 to t. We have proven that it is a martingale. And we have also proven that the funny process yt, that is equal to 2 over 3 times st, is also a martingale. Okay, that we have proved on during the last class. Yeah, everything is fine. Do you remember?
Yes.
Yes.
With the second group, we have used different numbers, but the logic is the same. So you just change 0, 4 and 0, 6 by, I don't remember, it was 0, 3, 0, 7 or something else. Okay, this will influence. So we have used different numbers that will influence modifications to obtain martingale, but the logic is the same. And my question now, we will use optional stopping time theorem. So my question now is to let's create a stopping time. Let tau be the first moment of time at which I will either reach st is equal to minus 10 or st is equal to 15 or maybe 20. I don't care. Maybe 20. So it's the first moment of time when we will leave a horizontal corridor, a horizontal strip. So if we draw, we have t, we have st, it starts at 0, and I will draw once again a continuous line, but my process is discrete. It's better to draw separate points, but it's too long. So it's going like this, and up, we have a strip of values between 20 and -10. And the first moment of time when we leave this strip is tau. Or to be perfect, the first moment of time when we touch the border of the strip. Okay? Yeah? It's more or less easy to check whether tau is stopping time, because at every moment I have enough information to check whether we have already reached the border of the strip in the past. My information, I observe the curve, so my information is sufficient to check whether we have already obtained the border. Okay, tau is the stopping time. And now my question is, what is the probability that S tau will be equal to 20? What is the probability that we will hit the upper part of the strip and not the lower boundary of the strip? And my second question, calculate expected value of tau. How long will it take to leave the strip? Okay, the question is easy. Sorry, the question is understood. So I'm not thinking about the solution. Is the question okay?
Yeah.
I'm not asking about how to solve it. I'm asking about whether what we are looking for is clear.
Yes.
Okay.
Yeah.
So now let's answer these questions by using optional stopping time theorem. First, let's check all possible values of S tau. Which are the possible values of S tau?
-10, 20.
-10, 20. It may be wise to know that it may happen that it is non-existent. Yeah. Imagine tau equal to infinity. So imagine that we always fluctuate inside the strip. Yeah. Sometimes it's not defined. Yeah. In this case, S tau is not defined. It may happen, but we can measure probabilities. So if we measure probabilities, so to be accurate, it may be -10, it may be 20, or if tau is plus infinity, so we never reach, we never leave the strip. So in this case, S tau is not defined, but we may prove that this bad event has probability 0. So it may be not defined, but it happens with probability 0. So we just ignore it, because if we put there any number, so instead of not defined 5, 7, -10, I don't care, because it's multiplied by probability 0. So I don't care about this case. But to be careful, we need to stress that for another random variable, it would be unwise to ignore this event, because in some other case, the probability of this bad event may be strictly positive. Okay, so let's call this probability P and 1 minus P. So I need to find one unknown. For the moment, let me blindly apply the theorem. I will not check these technical conditions A1 or A2 or A3. I will not check them. Let me apply the theorem. Let's suppose something is satisfied, A1 or A2 or A3. Yeah. And we can easily say which one is satisfied. Which one is satisfied? Let's go back. Which one is satisfied? If I consider this ZT, which one is satisfied?
A1?
No, A1 is not satisfied. Why A1 is not satisfied? Because you cannot be sure that we will leave the strip before in 10 steps. Yeah. What is the
Maybe the third one is satisfied.
Which one?
The third one.
The third one. Yeah, the third one is satisfied. Yeah, you're right. The third one is satisfied. The first one, why it's not satisfied? Because this tau is not bounded. It might happen that we spend 10 years in the strip and then we touch the upper boundary value. Or it may happen that we are in the strip for 1 million of steps and then we will touch the bottom line. It may happen. So you cannot say a priori that, oh, tau is less than 20. No, it's not possible. A1 is not satisfied in this case because A1 says you can state the number and for sure tau is less than the number you state. But if you look at A3, consider the difference of my martingale. What is my martingale? Let me look at my martingale. My martingale ZT, delta ZT, is delta ST minus 0.2. Yeah. Delta ZT is delta ST minus 0.2. And this is just XT minus 0.2. And this difference, for sure, it's between minus 2 and 2. Because X is either minus 1 or 1. And X minus 0.2 is bounded. So I can say that this random variable is bounded. It doesn't grow, it will not grow too fast, my ZT. So we have even checked A3, but I understand that the hardest part, sometimes the most technically difficult part is to check these technical assumptions of the theorem. So we will check non-technical assumptions that our process ZT is a martingale, ZT is a martingale, tau is a stopping time, A3 is satisfied, but it's the hardest one to understand, to check, hardest one. In this case, the theorem can be applied, and it says that expected value of Z tau is what?
Expected value of Z0?
Expected value of Z0. Yes, I may use here expected value of Z5, but Z5, I need to look at it. I need to understand it. And Z0 is very simple. Z0 is S0 minus 0.2 times 0, and it's just 0. Oh, I'm happy. So expected value of Z tau is 0. And what is Z tau? Z tau is S tau minus 0.2 times tau. So expected value of S tau minus 0.2 tau is 0. So expected value of S tau is 0.2 times expected value of tau. That's a very interesting equation, because this equation says that questions that I'm trying to answer are linked. If, for example, I would guess by somehow expected value of tau, then I would guess expected value of S tau, then I would guess probability that S tau is 20. Or if I have a way to find the value of probability that S tau is 20, then I would calculate the expected value of S tau, and then I would calculate expected value of tau. So that's great. Okay, and I also have an equation that expected value of S tau is -10 times 1 minus p plus 20 times p. So I have linked p and expected value of tau. So I need one more equation. Yeah. Where I can find this missing equation? Who can guess? Who can guess where I can find the missing equation?
Below, you stated that the expected value of S tau minus 0.2 tau equals 0.
Yes, we have used this equation. How many martingales do we have?
2 martingales.
How many martingales do we have? How many?
2.
2 martingales. Let's
Two.
apply optional stopping time to the second martingale. We have used the first martingale, ZT. Now let's apply the same theorem to the martingale. To the martingale YT. Yeah, I have another martingale. Do you remember? I have YT. It's also a martingale. So YT is 2/3 times ST. YT is a martingale. Tau is a stopping moment of time. Is a stopping time. Who can guess which one is okay? A1, A2, or A3 is satisfied for which assumption additional is satisfied for YT? Let me
Singularly
state
the third, because delta.
which one?
Singularly the third.
No, the first no.
The third.
Tau is a moment of time. Then we will reach when we will reach 20 or -10. Do you remember? Can you be sure that you will reach these two values, one of them, before, let's say, 50 steps? Can you be sure?
No, I didn't say first. I said third.
Third. Okay. Third. Bum 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 bum. Third. Yes, I think two are satisfied. The third and the second, I think, both are satisfied, because S. So let's consider S tilde. It's S tau, minimum tau, and T. So if we consider moment of time, this moment of time, minimum tau and T, is less than tau. Okay, so this moment of time is less than tau, and so I may conclude that S, this minimum tau and T, is between -10 and 20. We have not even, yeah, like this. So if I consider this random variable as before the occurrence of stopping time, so I can be sure that I'm still in the strip. Yeah, I'm in the strip, and if we put in, so Johnny Beck, I have just seen your question. Yeah, I will try to answer it in a moment. Okay, so, and if S is between this, if S is limited, so, okay, the absolute value of S tilde is bounded by 20, so A2 is satisfied, and A3 is also satisfied because difference is also limited. So the delta ST is also limited, let's say by, but it's obvious, it's limited by, I think by 2 or something like this. A3 is also satisfied. Okay, so we can apply optional stopping time theorem. And expected value of yt is expected value of y0. But what is y0? Y0 is 2/3 to the power
Of ST.
0.
ST.
0.
So it's 2/3 to the power 0. It's 1. So expected value of 2/3 to the power. So we know that optional stopping time theorem says that expected value of y tau is 1. But what is the expected value of y tau? It's expected value of 2/3 power y tau, and it's 1. Okay, sorry, s tau. Yt is 2/3 over st. I'm almost done. What is the value of s tau? We have noted that they are -10, 20, or possibly it's not defined, but this is probability 0. It's a good moment to answer Johnny Beck question, why it's 0. It's p, it's 1 minus p. So y tau, sorry, has the value 2/3 to the power -10, 2/3 to the power 20, and not defined. But I just ignore this case. Why it's 0? Because what is the probability that you will never leave the strip? It means you will never leave this. You will not leave the strip in the first 30 steps. You will not leave the strip. So it says probability of never. Probability that tau is plus infinity. Probability you never leave the strip. This probability is just is less than probability that you will not never leave the strip is probability is you will never leave the strip is probability that you will just a moment. Probability that you will never leave the strip is Imagine the following case, just a moment. Imagine the following case. If I go up, 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 if x1 is 1, x30 is 1, if 30 values in row are 1s, then I'm sure I will leave the strip. So if I have 30 values of 1 in a row, then I'm leaving the strip. Yeah, it doesn't matter, Johnny Beck, where I am now. 31s in a row are sufficient to leave the strip. So probability that I will never leave the strip is bounded by the probability that I will never see 30 ones in a row. So it is less than probability I will never see 30 ones in a row. And this probability that you will never see 30 ones in a row is a probability like 1 minus 0. So what is the probability that you will never see 30 ones in a row? It's 1 minus 0.6 to the power 30 times 1 is less than 1 minus 0.6 to the power 30, 1 minus 0.6 to the power 30, and so on. You never see 30 ones in a row, and even this probability is 0. So in our case, the probability that we will never leave the strip is 0. So that's why I do not care about the value of random variables at this bad event. Okay, and now I have explained why I have 0 in this cell. So it was a question by Johnny Beck. Now I move back to my question. What is expected value of 2/3 to the power s tau? With probability p, I get 2/3 to the power 20, and with probability 1 minus p, I get 2/3 to the power minus 10. And this expected value should be, according to optional stopping time theorem, the value should be equal to
1.
To 1. Yeah, you are right. This value should be equal to 1. And I can find p. I have sufficient equations to solve my problem. I can find p, I can find expected value of tau. Bingo. So let me write the equation for p. So once again, I will copy it here. Plus 1 minus p 2/3 to the power minus 10, it is 1. So I open the brackets, p times 2/3 power 20 minus 2/3 to the power minus 10 equals to minus 2/3 to the power minus 10 plus 1. And finally, I have p is equal to 1 minus 2/3 to the power minus 10 divided by 2/3 to the power 20 minus 2/3 to the power minus 10. So we have found p. And if you recall, the first equation was expected value of s tau is 0.2 times expected value of tau. So this is answer to the point A. And for the point B, we use the first equation, let's say that expected value of tau is 5 times expected value of S tau. It is 5 times P times 20 plus 1 minus P times minus 10. And it is 5 times 20P plus 10, 30P minus 10. And it's 150P minus 50. And P is that value I'm a little bit lazy to plug in, but P is here. So I have calculated the expected value of the stopping time. So how much I will wait on average before hitting one of the two boundaries of the strip. And I have found the probability that I will hit the upper line. Okay. So we have not started with winner process, but we have completed our example on optional stopping time theorem. Okay. Any questions?
I have a question.
Yes.
So we can apply optional stopping time theorem when one of the assumptions is correct, or they hold simultaneously. I didn't get it, because in the first case we were like, you said that the first one doesn't hold, but the third one holds, so we apply this theorem.
In the text of the theorem, it says at least one of additional condition is satisfied. So I have just checked them all, yeah, but it's not necessary. Just one is satisfied, you are fine. And even more because these assumptions are sometimes very difficult to check. So normally on the exams, like you check first one, check second one, and I say you can believe that one of the additional assumptions is satisfied, because otherwise the exam will be too technical and lengthy. So in practice, so the formal statement, at least one is sufficient. If you are speaking about the exam, and so because it's a little bit tough to check. In this case, we just ignore which one is okay. I say, so basically the answer, at least one, is enough.
Thank you, thank you.
So these are all necessary, first and second, yeah. First is necessary, second is necessary, and at least A1 or A2 or A3. Any more questions?
Yeah, Professor, I have a question.
Mm.
So do I get it right that having ST not the martingale formula, we can have countably many martingale formulas? Like we just managed to take into account two of them with the power.
Yes, you can create a lot of martingales, but sometimes it's a little bit tricky to create new martingales.
Yes, that is the main point, that we can create countably many variations of martingale having ST, and each one will lead us to this kind of probability.
No, it will give some equation that links different probabilities. Yes, it's
so. And why do we state that this probability is right?
I don't know, but equation will be different. But
equation will be different, but the probability will be the same.
No,
approximately.
You will have different equations for different probabilities. So if you provide another martingale, it will be equation, but that equation may involve other probabilities. I don't know, probability of expected value of tau squared. So for example, you can create some yes, you are right that we have used just 2 martingale, and I think you can create a martingale like MT of the form something ST squared. You can guess, I think, coefficients like alpha ST plus beta T. You can find alpha and beta to make this process a martingale. And if you apply optional stopping time theorem for this martingale MTE, a new equation, yes, you will have a new equation, but this equation will involve expected value of S tau squared. And using this martingale, you will be able to calculate variance of S tau. Yeah. Okay.
Mm-hmm.
So, it may, a new equation will involve new quantities, and if it involves new quantities, it will not contradict previous equations. Yeah, if you will construct 20 new martingales, you will obtain 20 new equations using optional stopping time theorem, but either they will be equivalent to old equations, either your new equations will involve new quantities and you will be able to find the new quantities, but there will be no contradiction. We have not proven the theorem, but believe me, I'm a honest man and it's true.
Okay, so we can state that this probability is right.
Yes.
For any
yes,
type of martingale.
Yes. If the
Okay.
theorem is applicable, so if A1, so if all the 3 conditions A1, A2, and 3 are not satisfied, then we cannot make an equation. Yeah. But yes, believe me, the theorem is true. You can Google it, optional stopping time theorem, and check.
Okay.
Can I ask you a question, please?
Yes.
Can you please just quickly show the answer on the A question? The probability that we will meet on the upper.
Yeah, here it is.
So this is the probability. And
Yes.
upper, why it doesn't depend on P?
On
Because on P.
On what?
On probability.
On which probability? This is the probability.
Look,
this is the probability that S tau is 20.
But we do not assume I mean the answer does not depend on the probabilities of V being equal -1 or 1, you know? I mean,
Why? It depends. Why? It depends. Because these 2/3 we have obtained during the class. And when we were obtaining 2/3, so if you change, it depends. So if you change, if you consider xt that has -1 and 1, let's say with probability 0, 1 and 0, 9, and in this case, you will have not 2/3, but some other number there, and this will influence these 2/3. It depends. This will be YT. It depends.
Thank you.
So other probabilities for X will give other value instead of 2/3. Yes. Okay. So if there are no more questions, then thank you. Have a nice day. Bye-bye.
Bye. Thank you.